we talked about Kw, which is the winding factor, which is actually Kd multiplied by Kp, because the winding is distributed and also you are not going to have a pitch of 180 degrees. So, this gave us the voltage equation, which is similar to a transformer equation, but we will have to multiply that by Kw. That's what we said as the voltage equation. After this, we actually looked at the basic principle of operation of synchronous motor and synchronous generator. So, we said that synchronous motor we are going to have doubly excited. So, it is going to be excited from both the armature side as well as field side. Armature is going to get a three-phase supply, field is going to get a DC supply, and field is going to be dragged along with the armature revolving magnetic field. So, the armature revolving magnetic field essentially drags the rotor along, and that is the reason why the rotor has to rotate at synchronous speed or it cannot rotate at all. So, if at all I am trying to start it, I have to start it in all probability with two of the methods. One may be using variable frequency, wherein I am going to give sufficient time for the rotor to catch up with, the stator revolving magnetic field. The stator revolving magnetic field is going to probably rotate initially at 1 RPM or less. Then it is going to slowly increase in its speed, because of which the rotor can be dragged along. That is what is going to happen in variable frequency starting. Whereas in the other case where I am going to use damper bars, which are very similar to squirrel cage rotor bars in an induction machine, these are going to be short circuited, because of which they are going to develop a small amount of torque, not a very large torque. So, I would call that torque as induction torque. So, these motors are induction, start, synchronous, run motors. So, these are the two methods of starting, and we also said that the major advantage of a synchronous motor. So, let me reiterate the advantages again. So, as far as the advantages of synchronous motor, I am not talking much about the advantages of generator, because you don't have any other option. You use only synchronous generator. If I have to generate a large capacity electricity power, then I have to use only synchronous generator. So, there is no point in talking about in what way it is better than induction generator, because induction generators are hardly ever used. They are not used very commonly. So, I am talking about motors. If you look at synchronous motors, one major advantage I am going to have is power factor control, because I am exciting it from both sides. So, the flux what I am providing from the rotor side can be just sufficient. It can be a little more than what is needed. It can be a little less than what is needed. So, I may be drawing a magnetizing current from the armature side. If I am having a shortfall in flux, I may draw no magnetizing current at all. If the flux is just sufficient, I might return some amount of reactive power to the three-phase mains if I am having excessive amount of reactive power fed from the rotor side. So, I will be able to make the armature behave like an inductor or capacitor or just a resistor, which is actually going to draw, the armature is going to draw, in which case only a unity power factor current, if it is behaving like a resistance. So, the current would be just sufficient to generate the torque, which is actually the real power component. Right. One more advantage we said was, because the power factor could be unity, right? I would say the current drawn, that is for a given power, for a given output power, synchronous machine draws less current. I would say rather may draw less current if I am working at unity power factor. Right? So if the machine is working at unity power factor, the current drawn, because I am going to say that root 3 VL IL cos phi, if I assume that the efficiency is almost unity. So root 3 VL IL cos phi is going to be the input power, which is also approximately equal to output power if I assume that the efficiency is almost unity, in which case cos phi in the case of induction machine has to be 0.8 or 0.85 at the most, whereas in the case of synchronous machine it can be unity power factor, due to which for a given voltage and for a given power IL will be minimum when cos phi is unity. Right? So I would say that the current drawn by the synchronous machine is generally somewhat smaller as compared to, I am talking about the armature side, of course. The current drawn by the armature will be somewhat smaller as compared to the stator current drawn by an induction motor. Normally at a given rating, both of the ratings are the same. If I look at the power factor, in all probability synchronous machine power factor will be much better or at least close to unity. One more advantage which I had not mentioned earlier is, if I am having the rotor and stator, the rotor is sitting inside the stator, the air gap has to be as limited as possible in the case of an induction machine, because I am providing the magnetizing current also from the stator side, and necessarily that flux has to link with the rotor if I want to generate a torque. If the air gap is more, the leakage will be more. If the leakage is more, to produce the same amount of torque, I might require the same amount of flux linking. If the air gap is more, I might have to produce more overall flux, so that the useful flux is still corresponding to the original quantity when the air gap was smaller. So I have to make the air gap as small as possible, so that the magnetizing current drawn in the case of an induction machine becomes really small as possible. So I can't afford to have a little larger air gap. Whereas in synchronous machine, I can afford to have a little larger air gap. If I have to do that, maybe there is some kind of load which is going to have a little torsional motion. It will rotate normally about an axis, but there may be a little, torsional motion which may go and hit the stator if there is not enough, leverage or enough margin available. So in the case of synchronous machine, I would be able to use those synchronous motors even in those loads where I may expect some amount of torsional motion or some amount of vibrations in the rotor. Whereas in induction machine, I can't afford to increase the air gap, because the more I increase the air gap, the leakage will increase, the power factor will become worse and worse. It is going to make the power factor much worse. So that is the reason why induction machines cannot have larger air gap, whereas synchronous machine definitely. So synchronous machines can have larger air gaps, because anyway it is not going to affect, this is not going to affect the armature current. Going to affect the armature current or armature power factor. Whereas it does affect the power factor in the case of an induction motor very adversely. So I can't increase the air gap in the case of an induction machine, whereas I can do that in a synchronous machine. Right? We said field can be varied and we are going to look at what is the generated EMF under open circuit condition of the armature. Yeah. See, in the case of synchronous motor, I am providing excitation anyway from the rotor. So I can increase the flux or decrease the flux essentially by adjusting the rotor current. I don't have to play around with the armature current or armature power factor. So the air gap will not affect the armature current or armature power factor. Right? So let us try to take a look at OCC once again. So in OCC, that is the open circuit characteristics or magnetization characteristics, what we talked about in the case of DC machine. What we are looking at is, if this is my field, right, and I am going to show it as though I am just winding it like this. It is not really wound that way, but this is the field, and I am injecting a field current here, IF, right, and I have an armature. And normally the armature of a synchronous machine is specified like this. It is a three-phase stator, similar to the induction motor stator. So what I am going to do is to measure the voltage, what is generated here, maybe line-to-line voltage, at synchronous speed, when the rotor is driven at synchronous speed, and I am injecting a current IF, which is a variable current. It's not a constant current. So I'm going to inject a current IF. So what I'm going to look at is how much is EG for different values of IF. This is what is the open circuit characteristics of the machine when it is functioning as a generator, clearly. So what I'm going to see is, basically maybe it will start at some value like this and then it will go into saturation. This is how it is going to function as far as the OCC is concerned. So I may get probably the rated voltage at some point like this. This is what is my rated voltage. So which means this corresponding field current will be rated field current. This is going to be my rated field current. That is how the rated field current is normally decided. That is going to be rated field current. Okay. Now, I have this open circuit voltage, right? Actually, when I am going to connect the load across these, so let us say I connect a three-phase resistive load. I am just showing as though I am connecting three-phase resistive load here. When it is a generator, obviously I am going to load it electrically. So I am connecting a three-phase resistive load here. When I am connecting a three-phase resistive load, each of them is going to draw a current which is probably IA. I am saying this is IA per phase because it is anyway star connected. Phase current and line current are the same. So this is going to be the per phase current which is being drawn by this load, all the three-phase loads. Now these are three-phase currents. If I have three-phase current in a space distributed winding, that will create a revolving magnetic field, definitely. So I'm going to have two fields in the air gap, just like what I had in the case of induction machine as well. Induction machine, I had one field from the stator. Another field was because of the induced current and induced EMF in the rotor. That was also three-phase. So both of them were revolving magnetic fields created by virtue of three-phase currents being pumped in through three-phase space distributed winding. In this particular case, I have one revolving magnetic field because of physically revolving magnet. The rotor is revolving physically, and that is at synchronous speed. So that is definitely going to create a magnetic field which is revolving in nature. The other one is due to the three-phase currents that are passing through the three-phase winding of the armature, which is also revolving in nature. Now both these things are going to definitely induce EMF in the stator winding itself. Please remember, stator winding is stationary. Both these fields are rotating at synchronous speed, because of which I am going to have both of them actually inducing EMFs of same frequency. The frequency will not be any different. The frequency will be different only if the two fields had been rotating at two different speeds. They are not rotating at two different speeds. So, I am going to have basically two EMFs induced at the same time. One is due to IF, which was injected originally, which created the magnetic field from the rotor side, which was already rotating at synchronous speed because of my prime mover. The second one is created because I have connected a load now. Until I connect a load now, that is not existent. So if I actually look at my armature equivalent circuit alone, I will have an excitation EMF or EG or EF. Generally, many of the books mention this as EF, this as EF. So let me also mention this as EF. EF is, yeah. This is the induced one. This is the induced EMF in the stator due to field only, not due to armature, only due to field. So I have an induced EMF which I am showing as a voltage source EF. Now after this, I am definitely going to have one more induced EMF which is due to the armature current, which I may specify as some EAR. Due to armature reaction, the induced EMF in the stator due to armature current itself. So, now when I look at the resultant, I have to look at the resultant of these two EMFs before I say what is there in the terminals of my machine, the armature terminals of my machine. This armature reaction EMF, actually I can specify as a reactance drop. As simple as that. Because after all it is due to flux. And if I say armature reaction, armature current is probably along this direction. The flux will also be along the same direction, roughly. So this is IA, this will be phi A or phi armature. Right? So the induced EMF is going to be, I can write it as minus EAR this way or plus EAR this way. It is essentially d phi AR by dt, multiplied by, of course, number of turns, blah, 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 all those things. So I am going to have basically the induced EMF, which will be lagging behind probably the current if I am taking this as a reactance drop, as simple as that. Reactance drop, always you are going to have the voltage leading the current. So I can take this as the drop across XAR, or let me call this as XM. So I am going to have a reactance which is specifying what is the amount of voltage induced in its own self, that is the stator winding itself, which is due to the armature current, that is its own current. So whatever is available here, I may call that as the resultant EMF that is available in the armature terminal. Right? And whatever flux originally I said, I assumed that IF created a flux and it was linking completely with the stator. It may not. There will be definitely leakages from either side. There will be definitely leakages from either side. If there is leakage, I have to show one more reactance which will represent probably the leakage which will not link with both stator and rotor. There will be definitely total flux produced if I say is 1 Weber. Maybe 0.9 Weber will link with both the stator and rotor. Rest of 0.1 probably will link only with individual member alone. In which case, I am definitely not going to see the repercussions of this in terms of torque production or power production. Whichever does not link both the members, that is a waste. So, I am showing this wastage, what goes away because of the air gap that is existing between the stator and rotor. All the flux produced by the rotor will not link with stator. Similarly, all the flux produced by the stator will not link with the rotor. So, I am going to have some amount of leakage. Now, I have resistance also. Armature will have some resistance definitely. So, let me call this as RA. Whatever I am drawing is per phase. Very clearly, I am not drawing it for 3 phase. Everything is per phase. So, even EF, what I am mentioning, should be per phase. So, this actually gives me the equivalent circuit of my synchronous machine in general, and this is what is available as VT, the terminal voltage. Now, whatever I have connected as RL, if I may call this as RL, I should connect that RL here. This is the load resistance per phase. Yes. RA is basically whatever is the inherent resistance of this armature winding. The armature winding is thick, it is made up of copper, all right, but still it may have 0.1 ohm or 0.01 ohm as the resistance, depending upon how much is the length and what is the thickness and so on and so forth. So, I will have a resistance drop. I will have some portion going as a wastage due to leakage, and rest of it what I am showing is actually the mutual that is existing between the rotor winding and the stator. One thing I want you guys to understand is, will the rotor winding have an induced EMF due to the stator flux? No. Why? It is rotating at the same speed. Exactly. The rotor winding will not have any induced EMF whatsoever from, the rotating magnetic field created by the stator, because the rotor is rotating already at synchronous speed. So, when the rotor winding is looking at the stator flux or the air gap flux, which is the resultant of the original revolving magnetic field flux created by the rotor, plus whatever is the new flux created by the armature current. Both of them are rotating at synchronous speed. So, obviously, the rotor will look at that field as though it is stationary, because the rotor itself is rotating at synchronous speed. The relative velocity is 0. So, the rotor will not, yes. Both are? They are rotating at the same direction, at the same velocity, whether the north and south. Whether they are aligned, they have to be aligned. One is north on this side, south on the other side. The other one will be south on the other side, north on this side. Obviously, they have to be that way. How can they lock up otherwise? You are getting my point. So, there will be a drop. And one more thing, Lenz's law should tell you this. If there is no drop, the voltage should have reached infinity. Obviously. The question is, why should you take this as a drop? So, you have to take it as a drop. Very clearly, what his question was that if both of them are rotating in the same speed, they should be additive. If they are additive, how can you take this as a drop? You have to take this as a drop because one more thing, IA, what I have taken, Right now I have taken this as a resistive load. Who says it has to be only resistive? It can be inductive, it can be capacitive. Depending upon that, the currents are going to have different phase shift. For example, let us say I am talking about IF like this. Maybe the EF induced EMF in the armature is at 90 degrees. Okay? The current what I am talking about in the armature circuit, it will be almost in phase if I am talking about a resistive load. It may be at lagging behind at some other angle depending upon whether it is inductive load. So if my IA is somewhat like this, then please note phi F is here, phi A may be somewhere here depending upon what is the reluctance offered and so on and so forth. So now I have to look at, please note that phi F and phi A may be rotating at the same speed, but they are not in phase with each other, not at all, absolutely not. The two fluxes are not exactly in phase with each other, not at all. So if I am having the north pole of, the stator revolving magnetic field currently at some position, say x equal to theta equal to x, I can't say the north pole of the rotor will be at the same position, not at all. Yeah. Okay, working of the generator is I am having a magnet created either by permanent magnet or electromagnet. Fine. So this magnet is being rotated at synchronous speed with the help of a shaft which is in the middle, which is attached to a prime mover. The prime mover is making sure that the rotor is rotated at a particular speed, synchronous speed. Now I have A phase, B phase and C phase windings here. So these are the windings which are shifted from each other by 120 degrees. So this is A dash, B dash and C dash. I am going to have induced EMFs in A dash, then subsequently after 120 degrees I will have it in B dash, then subsequently I will have it in C dash, and I am assuming that the air gap I have shaped or windings I have placed and all those things are sinusoidal in nature, because of which I am going to have a sinusoidal induced EMF in all the three phases. They are shifted from each other by 120 degrees. That's about it when it is on open circuit condition. If I connect a load on the armature, all these things are going to carry current. Until then it had only induced EMF, so I didn't have specifically three-phase currents flowing through this. Now when I connect the load, I am going to have three-phase currents flowing through these windings. The load what I connect can be inductive, capacitive, resistive, depending upon I may have unity power factor current, I may have lagging, I may have leading current. When I have these currents, they are going to create again a revolving magnetic field. These two, the resultant of these two will be the overall air gap flux which the armature will eventually look at. So although the armature is looking at the resultant of both the fluxes, I am trying to bifurcate them in the equivalent circuit. One portion I am showing as EF, which is confining itself only to the rotor flux. Another portion what I am showing as XAR or XM, that is actually talking about what is the induced EMF due to the armature currents, which I call as armature reaction or armature flux based induced EMF. So these two together actually make up for, I am showing that as a drop because what Tanay asked just now, I am showing that as a drop because you can't have even at unity power factor or whatever further and further addition of voltage. It is not possible to bring it over to infinity. So Lenz's law very clearly says this has to be in the opposite. So if I actually show it in the equivalent circuit, I should show if this is plus and this is minus, I have to show this as this plus and this is minus. Clear? So that is how we get this overall terminal voltage. I should be able to write this as, if this entire current is IA, I have to say EF minus IA multiplied by whatever is my XM plus XL times J plus RA. This is what is going to be my VT. Am I right? Because I am going to have RA and IA, of course, will be with the phase angle. Vectorial sum again. So if you look at it, let's go here to the phasor diagram. This is phi A, this is phi F, armature currents. To the field, due to the field, which is physically rotated. Exactly. Right? Any questions? Field current is actually DC. How can we show in a phasor diagram? Phasor diagram always shows all the vectors rotating at 50 Hertz. You can't show DC in phasor diagram. It's wrong to show a DC in phasor diagram. Please understand. Because we are showing relative shifts. Right? All of them are rotating. None of them are stationary. What we are doing is, the DC current, although is injected into the rotor, you are physically rotating it. So the DC current is not producing a revolving flux. You are physically rotating it to create a revolving flux. So you can look at the DC current as an equivalent per phase AC current in a three-phase system. So there is an equivalence we have to calculate, definitely. So rather than mentioning this as IF, let me mention this as IF dash. IF dash is equivalent AC current when I visualize the DC current from the revolving magnetic field viewpoint. The DC current is definitely having zero frequency. It is not a rotating phasor. It is not a rotating phasor. But I am looking at it from the viewpoint of the revolving magnetic field. That is the reason I am able to specify that damn IF as, a vector, phasor, rotating vector. I am able to mention it only because I am looking at this whole thing rotating at synchronous speed. So, although physically I am rotating the magnet, it is equivalent to electrically creating the revolving magnetic field. How does it matter? I am looking at a magnetic field which is revolving. So, I am looking at an equivalent AC current that would have produced the same strength of the magnetic field as I have produced now with the DC current, which I am rotating at synchronous speed. Right? There will be voltage drop, definitely the resistance will be there, but we are not unduly worried about it. If I have to calculate VIF, I have to say it is VF, whatever I am applying, VF is a DC voltage. VF is the DC voltage. And RF, which is the field resistance. So I should say VF divided by RF will be IF, which is a steady state current. I am not going to have any transients because I have placed one particular voltage. I am not disturbing it. I am giving that excitation for quite some time. As simple as that. Right? So, now if I look at the resultant, I have to look at the resultant of these two. This is phi F and this is going to be phi A. Now whatever is the resultant is phi R. Yes? I am looking at the two fluxes. I have taken the resultant. That's it. Just now we talked about it. We will not have any induced current in the field because the field is rotating at synchronous speed. It will not see any relative velocity. Both of them are rotating at synchronous speed. If I look at phi A or phi F, both of them are rotating at synchronous speed. So phi R will also rotate at synchronous speed. Orientation is different, you can see from the resultant. But all of them are rotating at synchronous speed. So if you sit in the rotor, you will see only a constant field. So where is the question of d phi by dt? Stator is actually stationary. I have not made the windings rotate, have I? No. Stator windings are stationary, that is the catch. Rotor is rotating. Stator, the name itself, because it is stationary. So stationary windings will get induced EMF. You just can't do anything. So it's a beautiful mechanism which was probably conceived again by Tesla. Because three-phase generation started only later. Initially it was all DC generation. What Edison did was all DC generation. He made a small power system within New York City, and they showed that DC transmission could be done. They lit up many streets in New York, and ultimately they also realized that the voltage drop is really large as you go to longer distances. Especially they were transmitting at very small voltages. So the currents were large as well. Voltage multiplied by the current was power, it was DC. So the currents were large as well. So there was a huge amount of drop that was taking place. And later on, Westinghouse and Tesla, with Tesla's brain, Westinghouse realized, Tesla kind of talked about transformer, then he came to induction motors, then he talked about three-phase generation. So all those things were, paving the way for AC transmission. All of them together. Yes. See, if I am having IF here, right, it is inducing an EMF not in its own self, it is in another winding. It is inducing in another winding. So I am showing the other windings induced EMF as though it is getting 90 degrees shifted because d phi by dt. So sine and cosine very clearly 90 degrees shift. So this is the induced EMF in the armature. Right? Now this induced EMF is now being connected to a three-phase load. If it is resistive, I should have shown this IA in phase with EF. Because it is inductive, I have assumed it is somewhat inductive, I have shown this at an angle which is decided by approximately whatever is the load power factor angle. Right? This is the load power factor angle. So this is my IA. IA and flux should be in phase with each other, its own flux. And similarly, IF and its own flux should be in phase with each other. We are of course neglecting hysteresis. Of course neglecting hysteresis. Hysteresis says the flux should lag behind the current. We are neglecting hysteresis, of course. And we are assuming that the currents are perfectly sinusoidal. They will not be sinusoidal if I am talking about magnetizing current alone. They will not be sinusoidal if I am talking about the magnetizing current alone. But armature current consists of mainly the load current. Hopefully it is fairly sinusoidal. It should not be a problem. Right? So I am neglecting hysteresis, saturation, all those nonlinearities I am neglecting, and I am saying that flux is proportional to IF and it is in phase with IF. That's it. So this is what is the phasor diagram basically for the machine, which I have not still included the equivalent circuit parameters. We will look at that as well. Okay. Let me probably redraw that equivalent circuit once again. This is EF which is the open circuit induced EMF in the stator side per phase. Okay? I have Xm, which was actually responsible for the armature EMF, which is actually perceived as a reactance drop. Okay? Now I have the leakage. Then I have the resistance. This is my Vt and here is my load. I am not showing whether it is resistance, inductance or capacitance. This is my load. So this is my per phase equivalent circuit of the synchronous generator or synchronous motor, in general synchronous machine. Now, these two put together, the leakage and Xm put together, we call that as the synchronous reactance excess. We call this as the synchronous reactance excess. Please note one thing. In transformer, in induction motor, Xm was coming in parallel. This damn thing is coming in series. So I'm going to have excess value to be really large. The leakage of an induction motor normally will be only 10 to 15% or even less. In fact, it will be 7 to 8% very often. I'm talking about per unit values. Whereas, in the case of transformer, it is only 3-4%. Right? In the case of synchronous machine, because your synchronous reactance is the magnetizing reactance plus the leakage together, I am going to have this to be a very large value. It can be greater than 100% sometimes. So you are going to have a very large value as synchronous reactance, which tells me when I calculate regulation, eventually the drop could be pretty large. So I would say the drop, I'm talking about the drop in that excess itself could be pretty large. So there are designs which try to minimize this excess to help regulation. There are designs which do not minimize excess because in case a fault occurs. What do you mean by fault? If suddenly a short circuit occurs at the terminals. What is going to limit the current? Only synchronous reactance. Resistance is really small in most of the machines because we want to have the efficiency as high as possible. Even 1% drop in efficiency or 5% drop in efficiency can cost a huge amount of power. We are talking about 400 MVA and so on and so forth. So 400 MVA, even 1% is 4 MVA. I don't want to lose out so much of power. So I would like to improve the efficiency as much as possible normally in synchronous machine. Because the larger the machine, we pay more attention to the design to make the design much better to maximize the efficiency. Because the impact of every percentage will be a huge amount of megawatt. That's the reason. So normally we are going to have very low values of RA in most of the synchronous machine. In fact, unless we are calculating efficiency, very often we will even neglect this. Very often we neglect this. So, if you are asked to draw simplified equivalent circuit of a synchronous machine, it's very simple. You will just say, this is EF, you are going to have a reactance which is XS, and that's it. This is Vt, which is available. That's it. As simple as that. This is the overall equivalent circuit of the synchronous generator or synchronous machine in general. Only difference would be that if I say this current is Ia, of course with the power factor angle, whatever it is, so Ia angle phi, whatever, I am going to have EF minus Ia angle phi multiplied by Jxs will be Vt in a generator. In a motor, it will be just the other way round. Right? Because I am applying Vt and what I am getting on the other side as back EMF or counter EMF is Ef. That will still be there. It's not that it is going to go away somewhere. So, I will have basically Ef equal to Vt minus Ia angle phi multiplied by Jxs. This will be true for a motor. Right? Now, if I draw the phasor diagram for this machine, okay, RA is generally very, very small. If Xs is like 100%, RA may be 1% or even less. So, when we are looking at RA plus Jxs, Xs dominates heavily over your RA. So, you can afford to neglect RA unless you are calculating the efficiency. Because the efficiency calculation will involve Ia square RA losses. Whatever is the loss there, you will have to take care of that when you are calculating the efficiency. So, this is important. And if you are talking about a motor, you will have to take the friction and windage losses and things like that. Similarly, if you are talking about a generator and starting off from the mechanical side, you have to say mechanical power input minus whatever is the friction and windage losses will be actually given to the machine as the mechanical power, which will be converted into electrical power. So, let us say this is my Ef for a generator. Maybe my current is somewhere here. Right? So, what I need to do is to first of all construct the triangle corresponding to Ia, Ra, if at all I am looking at resistance also. Perpendicular to that will be Ia, Xs. Please note Ia, Ra should be minuscule compared to Ia, Xs. Right? This is of course Ia, Jxs. That's why 90-degree shift we have shown. What is the addition of these two will be Ia, Zs. If I may call that a synchronous impedance. What I need to do is to subtract this Ia, Zs from here. This is minus Ia, Zs. Ef minus Ia, Zs will give me what is my Vt. Please note, Vt will generally lag behind always Ef in a generator. Please note that Vf lags behind and this angle is delta. Normally all the books specify this angle as delta. So, Ef corresponds to the induced EMF corresponding to your revolving magnetic field created by the rotor. Vt is the resultant magnetic field's overall induced EMF minus whatever is the drop. And you are looking at the whole thing as the phasor diagram for the generator. Okay.